I'm getting it.
Microanalysis. It's going to be given by Dr. Patrick Echlin, who I'm sure most everyone here who has any interest in biological microanalysis has either encountered or will encounter his work. Patrick has been active in the development and a pioneer in the field for many, many years. His work has touched on almost every aspect of biological microanalysis in both the preparative and analytical aspects, from freezing of biological material, the theoretical aspects of freezing, to cryosectioning, bulk analysis, and instrument development. It's a great pleasure for me to introduce Patrick to you and look forward to his talk.
Thank you very much, Dr. Salmon. Now, this is, as advisedly, is an introduction to biological microanalysis, and I'm going to presume very little or no previous experience. And in writing up this talk for the published proceedings, I have carefully not included any references in the text, but have included 3 general references at the end. And if you can understand some of what I'm saying today and then proceed through the 3 references I have given you, by the end of it, if you have persisted, you will certainly be brought up to stream knowing what microanalysis is all about. Now, X-ray microanalysis is a method of chemical analysis in which it is possible to directly relate the elemental composition of a small region of cells or tissues with their morphological appearance. And first of all, I'm going to review some of the interactions of the electron beam with the biological material and to discuss the processes which give rise to the characteristic and background X-ray photons. This will then be followed by the factors which determine the intensity and production of X-rays, and will include a consideration of the effects of atomic number, absorption, and secondary fluorescence have on the spatial resolution, sensitivity, and accuracy of X-ray microanalysis of bulk samples and of thin sections. I will then have a brief review of the energy dispersive and wavelength dispersive spectrometers, which are the 2 main forms of instrumentation used for collecting and analyzing X-rays. And it will be shown how it is possible to obtain both qualitative and quantitative information from the sample, and using 2 different quantitative procedures. That is the continuum method and the peak-to-background ratio method, and I'll discuss those in a little detail. Finally, I would like to stress the importance of the specimen preparation, and I'll give again, in the constricts of time, an overview of the limitations of the ambient temperature wet chemical preparative procedures and the advantages of low temperature methods of preparation, examination, and analysis. So if we can start. If we consider that X-ray microanalysis is a method of chemical analysis in which it is possible to relate the elemental composition of a small region of cells or tissues with their morphological appearance. This is what, in other words, you are doing the analysis in situ. Now, this analysis is achieved by focusing a very fine beam of electrons onto a pre-selected area of a specimen, and then in turn collecting, measuring, and analyzing the X-rays which are emitted. These X-rays are characteristic of the atoms which make up the sample. Now, don't be mistaken, it is elemental analysis. We're not really concerned about molecules at all, but elements. Now, the main advantage of this particular method is that the analysis is carried out in situ, and a photographic record can be made of the precise region which is being analyzed. Could I have the first slide? I think these may work without the lights being off. Now, to give you some idea of what we can do, this is nearly up to date. It was up to date of about a month ago. The minimal amount is a good at 10 to the minus 19 of a gram. The minimal weight-to-weight ratio of about 100 parts per million. The accuracy of 5%. The resolution is now a little bit better than 25 nanometers, and it is probably close to 10 or 15 nanometers. Now, that is about the best we can do. Now, we frequently can't get as good as that, but that is a sort of figure that we would like to aim to. Now, X-rays are emitted from any specimen which is irradiated with high-energy radiation, such as a flux of electrons or X-rays. And nearly all biological microanalysis, X-ray microanalysis, is carried out using a high-energy beam of electrons, which can be easily focused into the area of interest on the sample. The next one, please. And this is what happens. I hope you can see this slide. It's a little bit small. We have, in fact, an incident electron beam coming down here. This little volume here is what we call the interactive volume, and the X-rays which are coming off here and here are but one of many signals that we can get. I presume you are familiar with things like secondary electrons, backscattered electrons, but there's Auger electrons, cathodoluminescence, there are elastically scattered electrons and inelastically transmitted electrons. There is a whole lot of reactions which go on here. But for our purposes, we are only going to consider these characteristic and the Bremsstrahlung X-rays, which I will explain in a little bit more detail. So it means that this same beam of electrons here, which is used to excite this microvolume to give the X-rays, can also be used to give morphological information either via secondary electrons or backscattered electrons, or under some circumstances, cathodoluminescence of visible light. Can we have the next slide, please? Now, just to put it into context, the X-ray microanalyzer is but one of several high-energy beam electron methods that enable us to give information. I'm only going to consider this, but we ought to consider, and these have been discussed at various times during this meeting, backscattered electrons can give us chemical information, secondary ion probe analysis, laser probe analysis, cathodoluminescence, electron spectroscopy, and Auger electron spectroscopy. There is a whole armamentarium of different methods which can give us chemical information, and some have advantages, some have disadvantages. We are only going to consider the X-ray microanalysis. Now, in order for the X-rays to be produced, the energy of the incident electron beam or primary electron beam has to be greater than some minimum value known as the critical excitation potential. Now, this critical excitation potential increases with atomic number because most of the elements of biological interest are of low atomic number, i.e. Z between 11 and 20, that is, let us say sodium through to calcium, the primary energy beam usually needs to be no more than 10 to 15 kV. You don't need to operate at very high voltages. Can we have the next slide, please? Now, the interaction of the electron beam with the sample gives rise, the interactions of electrons with matter can generally be divided into two classes. First of all, there is the inelastic scattering, where the incoming electron, the high-energy electron, interacts with one of the orbital electrons, and the incident electron transfers energy in the sample with a very small change in the trajectory of the electron. Secondly, we have elastically scattered electrons, where there is a significant change in trajectory of the incoming electron without any substantial change in energy. Now, during the inelastic scattering of the electron beam, the X-rays can be formed by two distinctly different processes. First of all, we have the so-called characteristic X-rays. Now, the characteristic X-rays are produced when the incident electron beam displaces or removes inner shell orbital electrons, leaving the atom in an excited state with a vacancy in the electron shell. The vacancy is filled by an electron from one of the series of shells of orbital electrons which surround the nucleus. And these shells are designated K, L, and M, which decrease in energy the further we get away from the nucleus. Now, each shell has a set number of permitted energy states. The next slide, please. This shows you the K, the L, the M, and the N. And what I will show you in a minute, that an electron is displaced from one of these shells, leaving a vacancy which happens to be filled by an electron from another shell. So each shell has a set number of permitted energy states which may be occupied by the orbital electrons. The energy difference resulting from these electron transitions is emitted as an X-ray, characteristic of the electron orbital and the atom from which it was derived. The energy of the X-ray photon is the potential energy difference between the two orbitals involved in the transition and has an important bearing on whether or not it can be detected. The next slide. Now, this means that we have the K shell, the L shell, and the M shell. And we will see that as we go up in atomic number, we get, you see the energies that are coming off, they're very low energy down here with light elements, say 10 to 20. As we go into higher orbitals, you see that you would need an immense amount of energy to get out a K electron of something like gold or uranium. But what happens is that we get the K shell electrons, and then as we go up, we get the L shell and the M shell. Now, in biological microanalysis, we are nearly always concerned with only K shells. And in other words, we're looking at electrons, say, from X-ray photons in this region, from 10 round, let us say, maximally up to about 30. Very low energy X-ray photons, i.e. something from lithium or beryllium, which would be largely absorbed by the specimen. A few X-ray photons would escape from the light elements up to Z, atomic number 10, and many of these would be absorbed before they ever reached the detecting system. It is only when we get to such elements as sodium and above that there is a sufficient flux of emitted X-rays to make X-ray microanalysis a practical proposition. Now, there are ways of analyzing these light elements. They are being done, but they need somewhat more specialized equipment. Can we have the next slide? Now, this is one of the illustrations in the published account, and it illustrates, I hope, the different way we can get the different signals. Here we have the incoming electron here. Sorry, I'll use the arrow coming in here. And here we got one coming in here. It interacts and knocks out an electron from the K shell, and that electron is ejected. That leaves a vacancy there, and that vacancy is filled from an electron from the next shell out, which is an L shell, or it could come from the next shell out again from an M shell. So what happens is you get an energy drop, because remember there's an energy difference between here and here, and that energy difference is made up by a photon, X-ray photon coming out. So we would say the X-ray photon has come from a vacancy in the K shell here, this white electron, and has been filled from an electron from the L shell, so we refer to this as a K alpha X-ray photon. If the vacancy has been filled with an electron from the M shell, we talk about it as a K beta. And we can see here, as we go up in the scale, an incoming electron may have knocked out an electron in the L shell, and it would be filled, say, from an M, so it would be designated an L alpha. If it had been coming from the outer, say, the N shell, it would be an L beta. And you can go all the way out and get a whole family of different X-rays coming off. But the ones that we are primarily concerned with in biological microanalysis are the K alpha and the K beta electrons. So thus each element has a distinct X-ray fingerprint depending on the number of electron orbitals, a consequence of its atomic number. For example, nitrogen, atomic number 7, has only K and L electron orbitals, so can only yield K alpha X-rays. Phosphorus, which has atomic number of 15, has K, L, and M orbitals, so will yield K alpha and K beta X-rays. And calcium, atomic number 20, has 4 orbitals, so in fact will yield K alpha and beta, and indeed an L X-ray line. Now, the X-ray fingerprints for all the elements have been characterized and are available either as a table, slide rules, or more usually embedded in the software of the computer-driven analytical programs. Now, in the case of light elements, it is not possible to detect the L and M X-rays, although the K and L X-rays are a characteristic feature of most metals. The reason for the inability to identify or get the L and M X-rays of the light elements is that they have such low energy that they are absorbed either in the sample or absorbed in the detecting system. And very heavy elements such as lead or gold have a bewildering array of K, L, and M X-ray lines. The characteristic X-ray fingerprint for each element is the basis of the X-ray analytical technique, as there is a direct relationship between the intensity of characteristic X-rays from an element in the specimen and the number of atoms of that element within the irradiated microvolume. The next slide, please. And here's an example of some of the X-ray lines in the 0 to 10 keV range. We'll just have a look at, say, there is a sodium line. The sodium K alpha has an energy of 1041 electron volts. Phosphorus, the K beta, has an energy of 2.139 keV. Look at another one, say calcium, the K alpha, has an energy of 3691. And so these are all ranged. And you can see that there are, say, gold here. We don't look for an M line, beg your pardon, a K line, but we can actually get a gold line, an L alpha 2 at 9628. So the first thing that comes up that in this 0 to 10 range, it is not just the light elements that we find. We certainly find the K X-rays, but we have all these L and M lines from some of the other elements. And this is one of the problems when it comes to identification. Now, the other type of radiation, could we go back to one slide, please? Bit of a problem. So the continuum radiation, or background, or Bremsstrahlung, or white radiation, it is unfortunate these have a more or less the same term. If I just... We got the slide caught. Now, what happens, I'll just... Can you get it? Thank you. Whoa, back one. Very good. We've been talking so far of this incoming electron displacing an electron, giving us the characteristic X-rays. We also get the incoming electron, which doesn't actually interact, you've got a lot of energy, remember, doesn't interact with any of the orbital electrons, but comes very close to the nucleus. And this gives rise to the continuum X-rays. Now, as can be seen from this diagram, the primary beam electron may pass very close to the nucleus of the sample atom and experience a large change in direction, but only suffers a very small energy loss. In the majority of collisions, the energy loss is less than 1 keV, although the energy distribution extends all the way to the energy of the incoming beam. So if this is, say, coming in at 10 keV, you would have an energy distribution all the way right up to 10 keV. Most of these low-energy X-rays are either absorbed by the specimen or remain undetected by the X-ray analyzer. Could we have the move on a couple of slides, please? Right, and here's the continuum. We have this continuum. You see, it goes all the way down here to 0 and goes up to 10. But what, in fact, this is, we have the observed continuum, and this is what this is the actual continuum here. But this is the observed continuum because these X-rays down here have such low energy that they never make it either out of the sample or are absorbed by the detecting system. So that we get characteristically this whale, sleeping whale hump here, where we get a drop off towards 0, a rise, and then a drop away up here. But in actual fact, if we could collect all these continuum X-rays, they would in fact go all the way to 0, and we would have this curve there. So it can be seen that the X-ray production from the irradiated microvolume is primarily a consequence of both the characteristic and continuum radiation. In the next slide, please. So that we have under here the continuum radiation here, and sitting on that we have these characteristic peaks, absolutely marked. And I've just put in, say, magnesium, beg your pardon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium, and calcium. I have put in a peak here characteristically of a plant. For those of you who are not botanists, bear with me. Plants have very little sodium, but they have an awful lot of potassium. So that we have the characteristic peaks sitting on this background. And we, in fact, can use both of these bits of information, the information from the background and, of course, the information from the characteristic peaks to allow us to do X-ray microanalysis. Now, this slide shows the visible manifestations of these interactions as a spectrum of the background radiation overlain with the characteristic peaks of the elements which are sufficiently high up in the periodic table to be identified. Now, the intensity of these characteristic X-rays. Although the intensity of X-ray emission is linearly proportional to the beam current, not the voltage, to the beam current, a number of other factors also play a part, and their effects vary depending on whether the sample is in the form of a bulk sample, that is, will not transmit the incoming electron beam, or a thin section which will transmit the incoming beam with negligible loss of energy. The next slide, please. And here we can see what is making up this, the characteristic line, and here we have this hump, and this hump is made up of the white radiation or background, and this varies very much depending on whether this is a thick or thin specimen, and then other things like the electron signal, electron sigma, and cosmic noise, which really is something we have to live with for most of the time. The next slide, please. And that shows you an actual spectrum from some plant material. These two large peaks would be potassium and phosphorus, and here is overlaying the characteristic, overlaying the background radiation. Now, could we move on to the next slide, please? Now, the intensity of X-rays in bulk specimens is dependent on three factors that I briefly want to discuss. The number of atoms that are encountered, the fluorescent yield, and the ionizing cross-section. Now, the intensity of these X-rays is proportional to the number of atoms encountered by the primary beam. That is fairly straightforward. The second one is this fluorescent yield, and this is the fraction of electron interactions which result in the emission of characteristic X-rays, the so-called fluorescent yield. Could we move to the next slide, but I want to come back. And the fluorescent yield actually does increase with atomic number. And you can see here we've got the K shell, and this is the ones that are going to be primarily concerned with biological microanalysis, the L and the M shell. So as we go up in atomic number, the fluorescent yield, that is the number of X-ray photons we're getting off per incoming primary electron. Could we go back one, please? And the ionizing cross-section, which is the probability that an ionization of the inner shell electron will occur. And this increases rapidly with the energy from 0 to the critical excitation potential, that is the enough energy that you need to put in to excite an X-ray. For example, the K-alpha X-ray of potassium is around about 3,300. You would need to put in at least 3,300 electron volts to even start an X-ray coming off. Normally you put in something like 3 times the critical excitation potential to make sure that you get a sufficient number of X-rays out of the sample. So those are these three factors: the number of X-rays accounted, the fluorescent yield, and the ionizing cross-section. Now, below this figure, the X-ray yield drops away very rapidly. Above this figure, there is no improvement in X-ray emission, and the primary beam, because of its energy, will penetrate deeper and deeper into the sample. And this penetration has two important consequences for X-ray microanalysis. The next slide, please. The further the beam penetrates into the sample, the larger the size of the volume from which the X-rays are emitted. The next one, please. Here we can see this is a bulk biological sample, and you can see here that at 7 kV we have a small interactive volume. At 15 kV, more energy. There is much further penetration. And this means that we're going to get our spatial resolution. In other words, the microvolume from where we're getting information will change quite considerably. And you can see within thin sections there is virtually no difference, because this interaction follows this characteristic teardrop configuration, and there is a neck here and thin sections here. This is why one has a much better spatial resolution. So we have the spatial resolution, and the second problem is the deeper the electrons penetrate into the sample, the longer the path length for the X-rays, many of which are absorbed by the specimen. Now, absorption is a particular problem for the light elements, and for this reason, the voltage of the primary beam for bulk samples should be no more than 15 kV. And these figures show the effects in both bulk samples and thin sections. Now, in thin sections, most of the electrons go straight through the sample without any loss of energy, and the absorption is negligible. Just to make sure you understand about absorption, the electron beam can come down to here, excite an X-ray down here, say of sodium, and the sodium X-ray only has an energy of about 1,000 volts, and then it's got to make its way all the way out of here, constantly banging into other molecules and atoms, losing energy all the way out, and it probably gets no further than there and never makes it out. A ballpark figure, say in a bulk sample, we may lose as much as 50% of the X-rays that are generated. Only 50% of them actually make it out and are detected by the system. Now, in thin sections, most of the electrons go through the section without loss of energy. Now, the production of X-rays. The first golden rule of biological X-ray microanalysis is that the X-rays generated within the sample are not necessarily the X-rays emitted from the specimen. I'll repeat that. The X-rays generated from the specimen are not necessarily the X-rays emitted from the specimen. And there are two cogent reasons why this should be so, and are dependent on three interrelated factors: the atomic number effect on the generation of X-rays, the absorption of the primary X-rays, and the fluorescent effect resulting from the secondary production of additional X-rays. The next slide, please. The next one again, please. Sorry. Atomic number effect, absorption effect, fluorescent effect. Now, the atomic number effect. This is a measure of the backscattering of the primary beam from the surface of a bulk specimen and the amount of stopping power of the specimen matrix. Now, the latter, that is the stopping power of the matrix, is important in determining how many characteristic X-rays are likely to be generated before the energy of the incident electron beam decays to zero. In biological X-ray microanalysis, the atomic number effect has only become a problem with the instrument if infrequent bulk samples of high atomic number. So for biological material, and certainly for thin sections, the atomic number effect is, in fact, of very little importance. The absorption effect here, the primary generated X-rays passing through the sample are absorbed exponentially with distance. And this can be a problem with bulk samples where low energy X-rays are generated deep in the sample. In thin sections, absorption is negligible. The next slide, and I'll need to come back. We can see here that the absorption is enormous down here with these light elements. And you can see here, generated with generated X-rays curve A's and the emitted X-rays curve B, you're getting a lot of the electrons, particularly at the light atomic number, are absorbed and never make it out of the sample. Now, the fluorescent effect, this is where the generated X-rays have sufficient energy to interact with other inner shell electrons of the specimen and produce secondary X-rays of lower energy. Now, this is really only a serious problem for bulk specimens where there is a small amount of high atomic number material in a low atomic number weight matrix. For example, if we had iron within biological material, we'd excited an iron X-ray, that iron X-ray would have enough energy to excite other X-rays and can give you quite spurious information. Now, to consider the, the fluorescent effect is negligible in biological material. So could we just go back one slide, please? And back, please. So the atomic number effect and the fluorescent effect is of little consequence in biological X-ray microanalysis, bearing in mind there are one or two exceptions, but the absorption effect is of great importance and we need to consider it a little bit more detail. Now, the spatial resolution, could we move on a couple of slides, please? The spatial resolution, and again, please. The spatial resolution in bulk samples depends on the volume through which the electrons diffuse and spread in the specimen. And you can show that the spatial resolution is dependent on first of all, the density of the sample. And I've taken here a frozen hydrated cell with a density of about 1.15. And you can see these colored teardrops show you the size of the interactive volume, and in turn gives you some feeling for the spatial resolution that we can get. You can see calcium X-rays from a 10 keV incoming electron beam has a much smaller interactive volume than the calcium that we would get from a 15 Ke electron beam. And you can see sodium at 15 kV using a spot, or sodium with a 1 micrometer raster. These will vary. Thus, for a given accelerating voltage, the spatial resolution is much lower in bulk biological material and would be between 1 and 3 micrometers. In most biological thin sections, the mean atomic number and density is so low that the beam spread is negligible, and the spatial resolution depends here primarily on the beam diameter. And in these circumstances, in thin sections, the spatial resolution would be typically anywhere between, say, 15 and 100 nanometers. Could we move on a couple of slides, please? Now, the specimen surface topography. X-ray photons travel in straight lines, and care must be taken to ensure that there is a direct line of signal between the region of the specimen being analyzed and the X-ray detecting system. Whereas most metallurgical and geological samples can be prepared with a very smooth surface, this is rarely the case with bulk biological specimens, and surface irregularities can easily obscure and absorb emitted X-rays, as can be seen from here. Here's our X-ray detector, here's the incoming electron beam, and we're getting electrons, but there's a huge, great mountain between where the X-rays are being generated and emitted and where they're being detected, which would mean that there will be a substantial absorption of X-rays by the specimen itself. Now, the X-ray collection efficiency can be substantially improved by tilting the sample towards the detector. Now, surface topography rarely presents a problem with thin sections, which are assumed, sometimes erroneously, to be absolutely flat. The next slide, please. So we would got here a nice flat specimen. There would be nothing in the way of the detector here, no surface irregularities. In terms of the production, collection, and as we shall see later, the quantification of X-rays, it is preferable to use thin sections rather than bulk samples. There are minimal problems with absorption, the spatial resolution is improved, and the quantitation is much more straightforward than with bulk samples. However, bulk samples are much easier to prepare, and when this preparation is centered on one of the low temperature methods, there is a much greater degree of certainty of retaining the elements of biological interest than in thin sections. Now, the instrumentation. The next slide, please. Two pieces of equipment are needed to carry out X-ray microanalysis. First of all is a source of high-energy electrons, and we have a whole range of ways of doing this. An SEM with an ED detector, or the WD detector, or a TEM with one of these, an old microprobe, and that should be an E there, where you are primarily dependent upon light optics to do your morphology, a new microprobe where you have electron optics, and then some of these hybrid machines, the TEM stem and the SEM stem. All of these give a beam of electrons that we can focus onto a known part of the sample. The only requirement of these instruments is that they can produce a narrow beam of electrons which can be brought to focus at different points on the specimen. Two features of the X-rays, their energy and their wavelength, are the principal determinants behind the design of instruments to detect, measure, and quantify the X-ray photons. The next slide, please. First of all, we have the wavelength detecting system. And I'm going to only very quickly go through this, because just to give you a feel of what it is. Here comes the incoming electron beam. X-rays are given off in all directions. We then put a diffracting crystal, and this is dependent on the so-called Bragg angle. The X-rays come in, and depending on what type of crystal you've got here, certain X-rays, and only certain X-rays, are reflected to some sort of detector. We don't really need, in this introduction to biological microanalysis, to consider what goes on here, but the rest of this is simply assistance for amplifying the signal, and then for sorting out the signal, and then counting the signal. Could we have the next slide, please? Here is a little bit more detail. The incoming electrons, the outgoing X-ray photons, incoming X-ray photons coming into the crystal being bounced off. So you can see here is the X-ray, here is the electron beam, here is the source of electrons. They're going off in all directions, but you put a crystal up here to reflect a proportion down here to a counter. Now, these X-rays come off as a wavelength, and these are why these are called wavelength detected electrons. And there is the X-ray resolution is excellent, and is equivalent to something between 1 and 10 electron volts, which eliminates many of the problems associated with the characteristic peak identification and overlap, which I will come to later. There is a direct relationship between the wavelength and the energy of X-rays. It is given simply by a formula that I have put in the proceedings, where the energy in keV times the wavelength in angstroms equals 12.396. But you can actually convert X-ray energy to wavelength quite easily. The peak to background ratio is much higher in wavelength detecting system, which improves the limits of detection. And certainly the light elements down to Z equals 4 are much easily detected. However, these advantages must be set against a number of limitations. The overall efficiency of collection, i.e. the proportion of X-rays measured to the X-rays emitted, is low. Now, this may be improved either by increasing the beam current, which has the problem of damaging the samples, or increasing the probe diameter, which will decrease the spatial resolution. There are long analysis times, typically between 30 and 60 minutes, which too can result in damage to the specimen. But the major limitation is that only 1 or 2 elements can be analyzed at a time, because you only would have 1 or 2 crystals here. So this might be the crystal where you're only going to deflect, say, the sodium X-rays. So you'd have to count for a certain period of time to collect the sodium X-rays, but you might have another crystal here for detecting, say, the chlorine X-rays, which you could do in turn. The next slide, please. This shows you some of the crystals. Typically, you see a quartz crystal would use for somewhere between phosphorus and zirconium, a lithium fluoride, potassium up to indium. You just have the choice of these different crystals, which you will sort of tune in, and depending on what you were doing for analysis. The next slide, please. Now, the more frequently met type of instrumentation is the energy dispersive systems. These instruments take advantage of the fact that the X-ray photon also have quite discrete energies. We were talking about this a little earlier. The detector is a lithium-drifted p-type silicon crystal, which converts the incoming X-ray photons into a series of variable electrical charges, which can be amplified, measured, counted, and quantified. The next slide, please. Oh, no, keep that one there. Here is the system here. The incoming electron beam, X-rays are giving off, and here we have the detector. Here is the detector here. It's normally put behind a very thin beryllium window. It's kept cold and at a vacuum. It's kept cold primarily so that this preamplifier, a so-called field effect transistor, has a very low noise. This is all kept cold by a liquid nitrogen dewar, so you can easily identify which microscope has got an energy dispersive system because it's got the large dewar on the back. And all we've got back here is simply a black box, if you like, for sorting out what these various X-rays are, putting them into the right bins in a multi-channel analyzer, and counting them. Now, I'm not going to go into any of the details here. It's not necessary in this preliminary introduction. Now, the presence of the window, the beryllium window in the front here, prevents the cold detector from becoming contaminated and absorbs the backscattered electrons. The window also, unfortunately, absorbs some of the light element X-ray photons, which limits the usefulness of these detectors for analysis below sodium. However, there are so-called windowless detectors and thin windows, which obviates many of these problems. And if you've been to some of the meetings, some of the sessions, there was one yesterday where the people from the Link system had shown quite conclusively that they were able to detect even elements as low as beryllium using these energy dispersive systems. Now, the advantage of the energy dispersive system is, first of all elements can be analyzed simultaneously. Secondly, the analysis time is very short, typically between 2 and 5 minutes. The overall efficiency of collection is improved because the detector can be moved to within a few millimeters of the sample and thus intercepts a much larger solid angle of X-ray photons. A consequence of this improved efficiency is reduced beam currents, smaller probe sizes, which gives us less beam damage and improved spatial resolutions. However, the energy dispersive analyzers also have their limitations. The X-ray resolution is poor, somewhere between 150 volts compared with, say, 10 electron volts for wavelength dispersive systems, and this decreases with the increase in the energy of the X-ray photon. Although this creates problems with the identification of all the peaks, spectral overlaps, and poorer peak-to-background ratios, and hence poorer minimal detection limits, these effects can partially be alleviated by using computers to gently massage the resulting spectra. The very low energy X-ray photons are absorbed by the beryllium window, and at high rates of X-ray production, the counting statistics and subsequent processing of the signal may give rise to a series of spectral artifacts, which I will briefly consider later on. Can we go through the next slide, please? This shows you the configuration of the dewar, and the detector is here. This pokes into the column of the microscope. The next one, please, which I think shows the... Here is the detector. Here is the window here. This is typically a beryllium window, but there are systems where you have a little turret that you can move in either a thin window here, a beryllium window, or have it absolutely windowless. Of course, without a window, you get the lower energy photons. We don't really need to consider here, but what happens is that the X-ray photon comes in here and is changed into a charge, and this charge is taken out. It means the main advantage is that these X-ray photons that are coming in here, you can collect all the X-ray photons that are being at least coming here, but they may not necessarily be all the X-ray photons being actually generated within the sample or even emitted by the sample. I'll come back to that in a moment. Ideally, biological microanalysis should be carried out on an electron beam instrument fitted with both types of spectrometers. Say, have a wavelength dispersive for some of the light elements, and then have one of these energy dispersive for the wide range. The high spatial resolution and improved limits of detection, particularly with light elements of the wavelength analyzer, would complement the multi-element analytical capabilities of the energy dispersive systems. Now let's consider the process of X-ray microanalysis. Could we move on to a few slides, please? And again, please. Once more. Just briefly, a comparison here between the wavelength dispersive systems and the energy dispersive. Let me make up the principal points. The resolution here is better with the wavelength 5 eV, equivalent of 5E, and say 150 eV with the ED system. The count rates here, you need fairly high count rates, or you can get away with very high count rates, much less with the ED system. The probe size is much larger with the wavelength, which means the space resolution is less good. It is much better with the ED system. Collection time, tens of minutes with the WDS system, minutes in the ED system. Spectral artifacts are rare with the WD system, are major ones, and we are going to consider some of these now. The next slide, please. Now, some of the things we have, the problems of collecting the X-rays. To the novice, the process of X-ray microanalysis can be fraught with difficulty, although these difficulties are readily overcome once they are recognized and appreciated. Now, these difficulties center around the second golden rule of microanalysis, which states that the X-rays emitted by the specimen are not necessarily solely those collected and analyzed by the detector. A golden rule is worth repeating. The X-rays emitted by the specimen are not necessarily solely those collected and analyzed by the detector. This rule that implies that the total X-ray signal is either not representative of the sample, in that certain signals are deleted, and or contain spurious signals which are not derived from the specimen. The principal reason for the loss of X-rays are faulty specimen preparation, absorption that we've already concerned, either within the specimen or due to poor specimen detector geometry. And we can talk about the so-called takeoff angle. Here is a high takeoff angle, as distinct from a low takeoff angle, and also the closeness of the detector. The closer the detector comes to the sample, the greater the acceptance angle and the more X-rays it will intercept. I think this will be seen in the next slide. We can see here the X-ray detector here and here and here. The closer it gets to the sample, the more of the X-rays it's going to detect. This can be an advantage and a disadvantage. So we need to consider the so-called takeoff angle, a high takeoff angle versus a low takeoff angle here. And consider it, if you like, make the analogy of looking at this surface with your eye. You will see more of this surface if you're looking at directly above. you'll see very little of the surface if you're coming in directly at right angles. And a compromise is, in fact, normally at about 45 degrees. They vary depending on the instrumentation. Now, these spurious signals are derived from additions made to the sample during preparation, such as fixatives, buffers, stains, and the thin films of coating material, and scattering from the regions of the microscope immediately surrounding the specimen. I think the next slide will show that. The next one, please. Here's a good example. Electron beam, here is the detector, and we can see that some of these electrons are bouncing off the specimen's support, the grid, the film, and all of these too can go into the X-ray detector. So we got the problems of some of the X-rays being absorbed in the sample and never making it out, some of the X-rays coming from the sample which are a result of faulty preparation. In other words, if you had used a lead stain, you are surely going to get lead X-rays coming off, and then all the spurious X-rays from the environment in which the analysis is going on. And we can, in fact, do something about this by using either metals of very low X-ray production, such as beryllium, or by putting lots of carbon dag over all these offending surfaces so that there is very little backscatter. Could I have the next slide, please? Now, at best, all these spurious signals can be eliminated, at worst, considerably alleviated. Now, the types of analysis. X-ray microanalysis can be carried out at varying degrees of sophistication. In many instances, it is sufficient to perform a simple qualitative analysis in which the presence or absence of an element is confirmed and directly related to a morphological feature. The information can be obtained either by mapping the distribution of the elements. The next slide, please. I'll have to go through these rather. Can we just go through several rather quickly? And again, yeah. And again. And again. Now the next one, I think. We can get it either by making an X-ray map. Here is a piece of wood that has been impregnated with a copper preservative, and here is an X-ray map. And you would say simply there are more copper X-rays in this region and less copper X-rays in that region. That's all you can say. Or you can run a line scan across the surface, and in this particular region, this again was for copper, it goes up, indicating there are more X-rays. And all you can say with this type of qualitative analysis is that there is more X-rays, there are more X-rays, or less X-rays. The next one, please. Or by carrying out a digimap. Here is, this in fact is the distribution of some sodium, distribution of potassium on some cellulose fibrils, and where we have these regions here and here and here, in other words, the reds, the yellows, and the whites are indicative of high amounts of potassium in a much lower region here. So there's a little bit of potassium here, and in this background here, much less. Now, at best, this approach can tell you that some region of a sample contains more of an element than another, and at worst, that an element is either present or absent. Now, in quantitative analysis, some analysis requires a more sophisticated approach in which detailed information is needed on either the relative or absolute concentrations of elements in the sample. And this is referred to as quantitative analysis, and requires considerable attention being paid to specimen preparation, the process of X-ray acquisition, and the way the ensuing data is corrected and quantified. A wide range of quantitative procedures are available for converting the collected X-rays to relative or absolute concentrations. And we just won't have time to go into these, but I would briefly like to consider the two general methods. The first of these is the continuum method for thin sections. And the quantitative procedures for thin sections is reasonably straightforward, because in nearly all biological thin sections, the measured X-ray intensity is proportional to the amount of elements in the analyzed microvolumes. The more X-rays you got, the more of the element that is present. The very thinness of the sample precludes any absorption of generated X-rays, and the fact that most biological samples are of low atomic number, the atomic number and fluorescent effects are, as I've indicated earlier, negligible. The spatial resolution is good because there is little beam spread within a thin sample. The quantitative procedure simply combines two well-known established relationships of X-ray optics. First of all, the intensity of the continuum, or background radiation, is proportional to the total mass thickness of the analyzed microvolume. And secondly, the peak intensity of the characteristic X-ray radiation of an element is proportional to the concentration of that element in the analyzed microvolume. Thus, this first relationship gives you a measure of the total size of the microvolume, and the second one gives a measure of the concentration of elements within that same microvolume. We can move a couple of slides. There's one equation which I'll just go through. Here is the equation, which just simply says, this is the so-called Hall equation or continuum. The concentration of, say, element X in the specimen is equal to the intensity of the X intensity of characteristic X-rays divided by the white radiation in the specimen over the intensity of element X divided by the white radiation in the standard times the concentration of the standard, which you would put in, and then this so-called G factor, which is a measure of the composition of the matrix. That is, all the composition of the elements that you can't analyze: carbon, hydrogen, oxygen, and nitrogen. And this is where the trick comes, is to get a very accurate, as far as possible, measure of the matrix. Either you make your standard up in a matrix the same as the matrix of the biological material, in which this G specimen over G standard just cancels out, or you very carefully calculate the matrix in the specimen. Using this equation, you can then use it to get quantitative information. Could we go back a couple of slides? And yes, a little bit further. The whole thing is dependent on sorting out the characteristic peaks from the background. We, in fact, really only want to collect a proportion of this peak, and we normally collect something which is known as full width half maximum. So you go half the way up this peak, the height, and then you say that's the maximum, and you make a little window, and what you're going to say is these are the X-rays I'm going to count. I'm not going to count these ones each side. This is a Gaussian peak. You only collect a proportion of these, and then you have the problem of making sure where the background. In something like this, there's no problem. Sometimes you have a high background here and a low background here. Most frequently, the background goes like this, a curve, and so that you have to have a series of rather careful spectral fitting routines, and so that you can very carefully remove the background. But these quantitative procedures work very well, provided you have got these characteristic peaks well separated. Now, the other analytical procedure which you use on bulk samples, could we move on a couple of slides, please? And again. And again, please. Yeah, back one. Back and again. Back again. This is the peak to background. Simply what you're doing is you are ratioing the peak to the background immediately below that peak. And it works particularly well for low atomic number elements in a low atomic matrix, biological material, where you've got a fairly flat surface, as you might have in a fracture surface, where you have no surface charging, and where you've got a quantified matrix. The next slide, please. Now, simply this works. The characteristic and background X-rays are collected in the same energy band. The absorption factor cancels out, as it's the same in the peak as in the background, which is immediately below. The atomic number and secondary fluorescence also is very low in biological material, and this too cancels out. It's very satisfactory where there is very little variation in sample density, as you might get, for example, in a frozen hydrated specimen. And simply the ratio of peak to background is used to give the percentage composition. Now, the details of these quantitative procedures are given, there's a little bit more detail in the written proceedings, and certainly in the 3 references I have given you, so that you can look at them at your leisure. Now, the accuracy of these 2 analytical techniques is very dependent on the care taken with the preparative method and the accuracy by which the X-ray spectra are deconvoluted. Most biological analysis gets to within 10%, which, although not as good as may be achieved with metallic samples, is still reasonable for biological material. The sensitivity does show some variation depending on the atomic number of the element being analyzed and whether the sample is a section or a bulk specimen. An average figure would be between 0.1 and 0.01% concentration. Now, in the last few minutes, I'd like to briefly go through the specimen preparation, because in biological X-ray microanalysis, this really is whether your analysis is going to succeed or fail. The quality of the X-ray microanalysis is no better than the attention paid to the specimen preparation, and this is nowhere more exacting than with biological samples. Without going into great detail, the method can be divided into those which rely on wet chemical methods and those which are based on low-temperature manipulations. In addition, most specimens fall into one of two main categories: thin sections, which by their nature allow high spatial resolution and more accurate quantitation. This must be offset against the difficulties of preparation, particularly with frozen hydrated samples, and an increased chance of specimen damage. Bulk samples are much easier to prepare, particularly with frozen hydrated material, and appear to suffer less damage during analysis. However, the spatial resolution is much less good and the quantitation less accurate. Now, the wet chemical procedures are based on the well-tried and tested methods devised for the morphological studies in different forms of electron microscopes. The approach revolves around the premise that the structure is a manifestation of the form and interrelationship of molecules and macromolecules in the cell, and that the specimen preservation should be aimed at stabilizing these organic building blocks. Now, while this approach results in images of consummate elegance and complexity, it does so at the expense of the smaller molecular species, electrolytes and atoms. From an analytical point of view, this approach is disastrous, as the methods both introduce foreign elements into the cells and remove vital elements from the cells. Could we move on a couple of slides, please? And again. And again, please. Here is an example from some work by Diana Harvey of the loss of chlorine, 36 chlorine isotope, from leaf segments during the varying stages of a wet preparative procedure. You can see as she goes here from the initial control at 100%, by the time we get down to embedding in resin, 80% of the sample, even some cases 95% of the sample, has been removed. A brief catalogue of the disasters occasioned by the set chemical approach should dissuade all but the most intransient and misinformed biologists from adopting this particular approach. Now, unless it can be shown very quite unequivocally that the given chemical-based preparative procedure causes no damage in the sample, then these methods should not be used for biological microanalysis. In a very few instances, specimens can be examined direct without the need of any preparation. Under these circumstances, the main artifact is that related to the distortions which result from air drying a highly hydrated sample. Now, the low-temperature procedures, there appear to be four main advantages. By lowering the temperature but still maintaining the liquid state, chemical reactions and transport processes of viscosity and diffusion are slowed down. This slowing down makes physiological processes, much more amenable to study. Water and many organic samples, when in the solid state, show a dramatic increase in mechanical strength and allows these materials to be sectioned, fractured, or dissected to reveal subsurface detail. There is a diminution in the amount of damage to the specimen. There is no need for any use of the deleterious chemical materials. I'm not going to go into the detail here, but there are a whole range of options that one can use. Can we move on a couple of slides? I think these might... back one, please. Essentially what we've got, if we take the tissue sample, these are the ambient temperature preparative techniques which I would dissuade you from using. The low temperature techniques essentially involve converting the water into a solid and then either going to, by a process of sectioning or fracturing, and then you can go through freeze drying, freeze substitution, and you can end up with material or stay in the frozen hydrate, as I and a number of my colleagues do this. You get a material where the elements stay in situ, and you get a material which you can see good morphological information. Generally speaking, if you adopt this particular route, you're going to get very good morphological information, but virtually no valid chemical information. If you go this route, you're going to get valid chemical information, but at the expense of poorer morphological information. Clearly, you would combine both, this for the morphology, and in some cases, certainly do this for the analysis, and in some cases, do this for information about the morphology. Now, can I move just to the last, if I can have about 5 more minutes? And again, please. And again. And again. And once more. Now, what I would advise any biologist, you need to establish some sort of protocol before you even touch the specimen. And this really depends on making your mind up what type of specimen it is, making your mind up whether it is a qualitative or a quantitative analysis. If you're really being asked only to say, is an element present, not how much, then you might get away with a less rigorous specimen preparation. Make sure you know what instrumentation you've got. If you've got an old microprobe, you may only have light optics, which is going to limit your spatial morphological resolution. You've got to make sure whether you're working with a transmission microscope, because it then means you can only work with thin sections. If you have a scanning beam instrumentation, then you can work with both thin sections and bulk samples. And of course, some degree of the sophistication. The next few slides will amplify on this. The types of investigations could be ranging from the natural physiology or the perturbed physiology, where you've added some drug to the system or there's some injury to the system. Most frequently, we do the morpho-analytical, trying to analyze, relate the analysis to a morphological detail. You can, in fact, do specialized microvolumes, where you take out small droplets of liquid from known areas or regions of the sample and analyze those outside the sample, and certainly the distribution of elements within a sample. The next one, please. Qualitative, semi-quantitative, or quantitative analysis. Make up your mind which of these 3 you're going to do. The next one, please. The types of sample: bulk, isolated cells, particles, liquids, or sections. You need to make answers to these. What type? Because there's going to be a different preparative procedure and analysis if you're dealing with a bulk sample than with a section. The next one. And the